This video is on projectile motion. So, what is a projectile? Well, a projectile is an object that is projected relative to the surface of the Earth. Now, it can be projected upwards or downwards or horizontally. The important thing to remember, though, is that the only force acting on it is the force of gravity. Okay, we're going to ignore air resistance, friction in this case, and just deal with the force of gravity acting downwards on the object. And there's three types of projectile motion that we're going to look at. In this video, we're going to talk about the first type, which I've diagrammed here. And what we'll notice is that we have an object which starts off some distance above the ground, and I'm going to say that this distance here is, let's say 9 meters. So it starts off 9 meters above the ground, and it's projected horizontally. So it's given a horizontal velocity of 6.5 meters per second. So the object travels horizontally, and gravity pulls it down to the ground. And the important thing to note here is that the initial velocity in the y direction is 0. Okay, so it's just got horizontal motion. There's no vertical motion to it. And what's true of all projectile motion is that there's two distinct motions. The horizontal motion in the x direction, and you'll notice that the x component never changes. It's always 6.5. So that's uniform motion. And in the y direction, where the y component is changing, it's getting longer, getting more higher in magnitude, that's accelerated motion. So horizontal motion in the x direction, accelerated motion in the y direction. So, typical question that we might be asked is, how far does this object travel in the x direction? Okay, that's the horizontal displacement, dx. And dx is also referred to as the range. Okay, so it's the range of the object. So how are we going to find the range of this object? Let me clear the screen and make our diagram a little bit smaller so we have some room to work. So I'm looking for dx, the range, and in that direction, the x direction, remember we have vertical motion, horizontal motion, sorry, not vertical motion. So we have horizontal motion. dx is equal to vx times t. That's the only equation we have for uniform motion. And in the y direction, we have accelerated motion. So in the y direction, I know that v0 times t plus 1/2 at squared will give me the vertical displacement. So my equation for accelerated motion in the y direction. And the important thing to remember is that the time in the x direction is the same as the time in the y direction. Right? It doesn't take longer to travel horizontally than it does to fall vertically. So looking at my equation for the uniform motion, the only piece of information I'm missing is the time. If I knew how long it takes to travel that distance, I could find the actual displacement here. In the y direction then, I want to try and solve for time. But I have time in two locations here, so that might be difficult. But what's important to remember is that this component here is 0. Right? So this part of the equation disappears, and it simplifies to 1/2 times at squared. And since I know the vertical displacement is -9 meters, it falls downwards, remember, so the negative is important. So it falls down 9 meters, and the reason it falls is because of gravity. Again, gravity is acting downwards, negative 9.80 meters per second squared. So I can get the time that it takes to fall. And that time, when I rearrange this and plug it all into my calculator, is 1.36 seconds. And now that I have the time, I can substitute that up here to get the displacement in the x direction. So in the x direction, it's traveling at 6.5 meters per second for a time of 1.36 seconds, giving us a displacement in the y direction of 8.8 meters. So I've now determined how far it travels in the horizontal direction using just equations that we used in grade 11 physics. Now, another question we might be asked is, what is the speed of this object right when it hits the ground? So not when it hits the ground and comes to a stop, but if we took a snapshot of it as it was hitting the ground, what was that speed? So again, we know that that speed, or that velocity, sorry, has an x component, which is 6.5, and a y component, which is going to be something quite large, giving us a final velocity. So I know the x component. What I need to find is the y component. So again, let me clear the screen. How do we find that final y component then? Well, I know that it started off traveling vertically with a velocity of 0, and then it accelerated downwards for a time of 1.36 seconds. So that y component is going to be a negative answer because it's traveling downwards, right? So again, the negative 9.80 is important. And it accelerated downwards for 1.36 seconds. So an object that travels under the influence of gravity for 1.36 seconds will have a final y component of 13.3 meters per second down. So that's the final component vertically downwards. And then I need to add those two components together to get the final final velocity. So the x component squared plus the y component squared. So the 6.5 squared and the negative 13.3 squared. And that ends up giving us a final velocity of 14.8 meters per second. Okay. Now, I said velocity, but that's not really the velocity. That's just how fast it's traveling when it's here, right? So we've determined the x and the y and the final v. So we've determined the magnitude of this vector. I also need to know the angle. So how many degrees below horizontal is that object traveling? So again, I use tangent of theta to determine that angle. The opposite side will be the y component, 13.3. Notice that I don't include the negative here because I'm just looking for an angle. I already know the direction. It's going to be below horizontal, so I'm not interested in the negative. And that angle works out to be 64.0 degrees. So my final velocity then is 14.8 meters per second at an angle of 64.0 degrees below the positive x-axis. You could also say below the positive horizontal. Either one would be correct. So that's our final velocity. And that's a typical projectile motion problem. We're using vector analysis to add x and y components. We have to do a little bit of algebra first to find the final y component here. But Because we're using components, it's a nice right angle triangle, and it's relatively easy to solve. So try out some of the practice problems in the homework, and if you have any questions, as always, you can track me down in class.